So, in this episode, we are going to cover Chapter 8, and we're going to talk about encoding, decoding, multiplexing, and demultiplexing. So, let's go ahead and get to it. So, the first topic we're going to cover is the process of decoding. And what decoding is it's converting some type of code, whether it's binary or BCD or hex or whatever, to a single output. Okay? So, if this is my decoder chip, without, getting into the nuances of what's inside the box, it's taking whatever's on the input. And so, like in this case, this is a 4-bit BCD decoder. So there's a BCD number on here. So it's 0000 through 1001. Okay. So there are some logic gates that are inside here that are making this happen. And so basically what you have is whatever number is on the input, you're gonna directly translate to a single output turning on. Okay, so I always think about because I try to look for mnemonic devices wherever I can, and so for decoding, I came up with decoding devolves into one output. So decoding devolves. So in other words, there's more bits here, and then you're only activating a single output. Okay, so it's almost like a selector switch, if you will. So, imagine that these are connected to various loads or maybe, different outputs, whatever they're connected to. And you put in some code on the front end to determine which one of these turns on, and only one of them turns on. Okay, so here's what it looks like. So this is for an octal decoder, and that's 3 bits. Right, so in the one that we looked at previously, that's a 4-bit, so that's a hex encoder. I'm sorry, that it's BCD, right? So there's 4 bits, but it is a BCD because we specify here. Otherwise, if it's just 4 bits, period, a 4-bit decoder, that's a hex. So here we've got an octal decoder, so we've got 3 bits. So there's the 8 possible combinations that can be on the input. And notice what happens. Only one of the outputs turns on. Okay, now this is for active high outputs. Active high, remember, is at rest, it's at 0, and when it goes active, it goes high. Active low outputs will have all outputs resting at 1, and then when you want it to be active, it will go to 0. And remember, the active low, any type of an active low switch or output or input is used because it helps to fend off some of that electromagnetic noise that might cause a load to accidentally go high. But if you get electromagnetic noise on a high, you can't make it more high. Okay, so but if you remove the voltage, then that's a definite change in state. So that's why we like to use the active low inputs and outputs. Okay, so this is sort of what's going on inside the box. You have the inputs over here. Like if I could draw a great big box, outside of all the gates, that's essentially what's going on here. So you're basically NANDing all of them together here. So it says complete octal decoder, active low outputs. And so if you wanted them active high, then you could just AND all of these together. So we can also call them, like a 1 of 8 decoder or a 3-line to 8-line decoder, because you can see here 3-line to 8, or choosing 1 of 8 possible combinations, right? So just different terminology that is talking about the same thing. And then here's some different IC chips. The one that we focus on in this class is the 7447 because that's a BCD to 7-segment decoder. And so we're going to actually use these quite extensively in Chapter 12 when we're writing to the 7-segment displays with our counters. Okay, so some more slides here on the configurations and the different IC chips. I'm not going to go specific on the 74138 this time, but you can see they're all accomplishing the same thing. You have inputs. And then here you have to have a certain enable input, and so you have to have a low, low, high. So you can see that in the previous example here. So you have to have a low, low, high for this thing to even turn on. That's to activate it. So just because you have something on here doesn't mean it's going to process it and turn an output on. Here is an enable input. So you can see here it doesn't matter if either one of these are high Or if this one is low, then everything stays high. Nothing turns on. It doesn't get activated until you have a low, low, high on E1, E2, and E3. Okay? And then it acts like the decoder, as you can see. There's a 1 of 10, BCD to decimal. Again, a couple more examples of these. All right? And they all have that characteristic, either high through the middle or low through the middle, depending on if they're active, low or active high. All right, so let's talk about encoding. So decoding, we said it devolves down into one single output, and encoding is exactly the opposite. So based on a single input that turns on, it's going to code that number on the output. So, and like in this case, octal input, only one of these is going to turn on, and that's going to activate all three of these. Okay, so this is, when I think about encoding my mnemonic devices, it enlarges to a coded output. So decoding devolves into one output, encoding enlarges to a coded output, right? So if the number 4 gets activated on here, the fourth one, then that's going to be 100, most significant bit, 100. Okay, so same thing. This one is a decimal to BCD decoder, so only one of these digits is going to turn on, one of these inputs, and that's going to put that number on the output. Okay, so that can be pretty handy when you're, converting between different systems and sending signals different places. Especially like I said, like a selector switch kind of deal. So decoding devolves down into one output. Encoding enlarges into a coded output. Right. So here you can see the decimal input and what it's going to put on the output. So this kind of just looks like binary and decimal, because that's really all that's happening, right? You activate one single input here, and then you get that on the output. So here's a decimal to BCD decoder for the most significant down to the least significant bit. And these are the inputs that are coming in. Again, you won't have to draw the decoder or the encoder like this. You just have to know how they operate. Okay, so priority encoding. So you may ask yourself, that's great if we have this encoder and only one of the inputs turns on. What happens if number 7 and number 4 and 0, because it's possible that all three of them could turn on. So what happens then? We have what's called priority encoding. Okay, so priority encoding says the highest input has priority, and highest meaning the biggest numerically. Okay, so back to my example where I said if 7 and 4 and 0 are all on at the same time, 7 is the one that takes priority because it's the bigger number, and it really just is from 0 to 7, lowest to biggest. Okay, so that's priority encoding. And again, we have more examples of these. So let's come down to what we call a code converter. So now we can convert from one number system to another, right? So we know how to do that by hand because that was the very first part of digital fundamentals, is that you learn the different number systems and how to convert between them. So we have a chip, or we have multiple chips that will convert from one number system to another. And that's all it's doing. It's converting a coded input into some other form, whatever it is. Okay? So here's a 3-digit BCD, and then, converting that and weighting each one and converting it into binary. Okay? So again, that's just working through the chapter 1 stuff that was covered a long time ago. One thing I do want to point out is one of the reasons to use what we call gray code, and we've talked about that, is from one position to another, only one digit will change. Okay, so that's why it looks like it's out of count, because it goes from 0, if we were talking about binary, 0 to 1 to 3, and then to 2. But in gray code, only one digit changes, from step to step. So normally in binary, if you're going from 0 to 1 to 2, from 1 to 2, you have the least significant bit flipped to 0, and you have the second least significant bit flipped to a 1. So 2 of them change in one step. So all this is doing is changing the next bit over, and then changing the one to the right, and then changing this bit out here, and then changing to the one to the right, and you just keep moving all the way around. So why we use gray code, and because only one bit changes from step to step, these are great to use in motor encoders. So it says gray code is used to indicate the angular position of a rotating machine. It varies only one bit from one entry to the next. So I could put a sequencer, a mechanical sequencer, on a spinning shaft of some kind of a motor, and it will turn on or it will encode based on where we're at here. And it'll walk through these different steps. And sometimes they'll shine a light from the other side, and the receiver on the other end will detect what pattern of these is turned on and off, and it will know what step in the sequence it's at. Okay, and so you can see there's a difference between gray code and binary code. I'm not going to make you count in gray. Okay, so let's talk about the next one. So we've got decoding, we've got encoding. Now we're going to talk about multiplexing. So here we're funneling several data lines into a single output for transmission to another point. Okay, so I liken this to watching cable TV. All right, so you have, as a paying customer, you have access to, well, now you have, if you have Hulu or something, you have hundreds and hundreds and hundreds of channels to pick from. And so what you're doing is you're tapping into one single signal and then putting it out to your TV screen. Okay, so that's not what's happening, but that's kind of the example I use, is that it mimics picking a station on your cable TV. So it used to be, before we had satellite and all this good stuff and streaming, you had 60 channels you paid for, or 90 channels you paid for, right? And so you have 90 separate inputs that you could potentially allow to go to your screen. You just have to choose one of them. And so it's the same concept with a multiplexer. You have a bunch of different data lines, and you determine which one gets passed through to the output. So these could be just about anything. They could be different input signals. Maybe this one is a 1K frequency, this one's a 500 frequency, 500 hertz, this one's 250, and this one's 125. So maybe you have a way to select different frequencies for whatever system that you're running. But that's what you're doing. You're selecting one single input and passing that and only that to the output. Now notice here you need 2 selection bits because there's 1, 2, 3, 4 combinations possible, right? And so you need to have 0, 0, 0, 1, 1, 0, and 1, 1 to select which one gets picked. Okay? So again, there's the truth table for the selector switches, or the select control inputs is what they're calling them. And so you have 4 different possibilities. You're going to choose one of them, and here's the combinations to get which particular one you want. Okay. So just for example, here's a 4-line multiplexer. So here's the first one. You can see that this kind of does what I was talking about. So this is a certain frequency. Let's call this one the 1K because it's the fastest. And then this one is half as fast. This one's 500, this one's 250, and this is 125 hertz. So each one gets progressively slower, and so on the select here, you're deciding which one of these you're going to pass through to your circuit. Okay, and there's TTL and CMOS versions. I'm not going to get tied up in these particular IC numbers. So now let's talk about the opposite of the multiplexer, the demultiplexer. So it's the opposite procedure from multiplexing. So now, when I think about this, it's like choosing a contact on your phone to call or text. So you are the input, right? So you are, like if I was talking to someone on the phone, my voice is the input, talking to the other person. Or, this could be like me broadcasting from a radio station, and and then certain places on the output will pick me up and funnel me through their device and listen to what I'm saying. So, but it's kind of like I choose a contact, one single contact on my phone, and then I call that person. And so my voice can only be heard, even though I'm able to connect to 500 other people that are in my contacts list. I only choose one, and I pass my input data through to that output. Okay, so you know, it just depends. It depends on which part of the circuit you want to activate with this input or why it's going to a certain location. But again, we have to have 2 bits for the selector switch because there's 4 possible outputs. If there were 8 possible outputs, then we would need 3 bits for the selector. So again, here's an input data signal, and then all we're doing is choosing which output we're going to route it to. That's it. Okay, I think that's essentially all I had to say about the multiplexing. One thing I will note is this staircase generator, and so this is something that we can do with a 74 HCT 4D51 staircase generator. And so what it's doing, what's over here, as you notice maybe from 111, if you your circuits class, is that this is one great big voltage divider. That's it. And so we have different node voltages at different points here based on the resistor values. And once these are, it says the voltage levels to be output. And so we've actually come up with this, which voltage is going to get passed through. And then we have, whatever we select to be output is going to be passed through the binary counter, or I'm sorry, the clock oscillator then goes to a counter, which will then change the selector from 000 to 001, 010, 011, 100, 101, 110, 111. It'll go through all those combinations and output each one of these a step at a time. And so this is the kind of the thing that you end up with. And then it resets itself and then outputs that voltage over and over and over. Okay, so again, each one of these is a separate input, and we're passing just one of them through, that's going to be on the output. So, we have a lot of different choices. It depends on what we put here that determines which one gets output. And obviously we do that in a pattern and in a sequence and have it do this over and over and over. Okay. So that pretty much covers chapter 8. A lot of this is conceptual. There's no real calculations involved. So just get these under your belt and then take the quiz. Thanks for watching.